So with this information, I can say that probability that x is greater than 50 is going to be 0.804. Okay, so this means that 80.4% score 50 or more. And the probability that they get 40 or less is 11%. Now, before I put this in on my calculator, before I use my calculator here, this first probability, I need to rethink of this as the probability that x is less than 50 is 0.196. And that's because I'm going to use inverse normal on my calculator in a second. And I need to think about it in terms of what is the area to the left of the 50, not the area to the right of the 50. Now, with this, I don't know what the mean is, and I don't know what the standard deviation is. Okay, so if I don't have one of those things, or in this case, if I don't have two of those things, I need to use the standard values. So I need to use z equals x minus mu over sigma. So firstly, I need to find out what z is. Okay, I know in both cases, I know what x is, but I don't know what mu is, I don't know what sigma is, and I need to find out what z is. So to do that, so I'm just going to quickly change my screen here. So to do this, I need to use inverse normal. So on my calculator, I'm going to go menu 7 and inverse normal. My area I put in is 0.196. So what am I going to put in for my standard deviation here? So this question I'm just going to ask you in the chat. What do I put in my standard deviation and what do I put in as my mean here? So just give you a few seconds. I'm gonna. No, normally I wouldn't have this up in the meeting at the moment, but 1 and 0, yeah, excellent. So I put in standard deviation as 1 and I put mu as 0. Okay, I'm talking about standard values here. So we get z as minus 0.856. And when I do that I'll write that in a second. And I also need to do it for my other value here for the 0.11. And I get minus 1.227 when I do that. So what I do is I put both those values of z that I just worked out into my formula. And you would expect both of these to be negative because you're both looking at values that are below the mean. So what we're saying is if you scored 50 on this test, that's 0.856 standard deviations below the mean. We expect it to be below the mean because 80.4% of people scored above that mark. So you know that scoring 50 on that test means you scored below the mean. So certainly 40 as well also means you scored below the mean. So what I then do is I can rearrange both of these equations to get the following. So if I rearrange the first one, this becomes mu minus 0.856 sigma equals 50. And the second equation, I would get the following. Okay, so all I've done there is multiply through by sigma and add mu to both sides and get these equations. So these are two equations that I can now solve simultaneously. And if you don't know how to do this, I will show you in the calculator. Some of you know how to do this already. But what we can just do is simply go on our calculator, press menu and then A. Okay, we'll just go down to equation / function. And then we just go 1 for simultaneous equation, 2 unknowns. I'm going to, instead of x, we've got mu, and instead of y, we've got sigma. So I just put in y and then minus 0.856 equals 50. Sorry, let's just change that. Minus 0.856 0.856. And then we've got minus 1.227, and we've got 40. So I get 73.1 for my mean. Okay, x is mu here. And for sigma, I get 27.0 to 3 significant figures. Okay, when we did the form, I asked you for it in for 3 significant figures, just to make it easier to input your answer. So I think one common wrong answer I saw from the form was, I think it was something in the region like 50 for your mean and something like 9 for your standard deviation. I think what you've done there is when you did the calculation for probability that x is greater than 50, I think what you might have done is just put in area 0.804 rather than 0.196. So I think that's what you might have done. Okay, let's get into part B then. Part B is a little bit quicker. To be admitted into university, a student must score better than at least 70% of the students that took the test and took the test and scored 102 marks. Will he be admitted to the university? So what we've got now is from our part A, we have the following distribution: mean is 73.1 and the standard deviation of 27. And we need to work out the probability that x is less than 102. So we just simply, on our calculator, menu 7, normal CD, put a lower limit of something like minus 1,000, upper limit of 102. Now we're just using the actual values for the standard deviation and the mean. And when we do that, we get 0.858. 3 significant figures. Okay, and then we just need to make some conclusions, such as so will he be admitted to university? Well, Adam scored better than 85.8% of students, so he will be admitted. Okay, make sure you got a conclusion there. It doesn't need to be any massive essay, but just something along the lines of that will be absolutely fine. You can also do this other ways. You could also work out what is that mark you'd have to get to be in that top 30% or not be in that bottom 70%. So there's other ways you can do it. That's just one of them. And then finally, we've got a hypothesis test. So it kind of brings together what we're doing recently. So in this test, we've now got a new mean and a new standard deviation. And we've got a random sample of 12 students. And the mean mark scored by those was 140. So your sample mean is 140. Your actual mean, which you believe to be true, is 160. But we're going to see if we've got evidence to suggest that's changed. So state your hypothesis clearly using a 5% level of significance. Test whether or not the mean mark obtained by the students this year has reduced. Okay, so firstly, I write my hypothesis. The first one, the null hypothesis, is that the mean is 160. The alternative hypothesis is that the mean is less than 160 because it's been reduced. It's just a one-tailed test. I'm only looking at the change in one direction, which is just that the mean is actually less. What my sample distribution becomes is that, sorry, not x, m in this case. M, put the little line above it to reference the fact I'm looking at the samples now. I have a mean of 160 and a variance of 50 squared, my standard deviation squared, over 12. Okay, remember your sample variance, you need to divide it by n, because the bigger your sample is, the closer your sample should actually be to what the actual mean is. So there's a few ways I could do this. I could do critical regions, But what I'm going to do is look at the sample of 140. Now, what is the probability of getting a mark of 140 or less if the mean is actually 160? Is it just a coincidence that we just so happen to pick our 12 students just so happen to get a small, a fairly small mark in comparison to what they normally should get? So work that out and see if it's significant or not. So yeah, again, calculate it, normal CD, and we get 0.0829. 0.0829 is greater than 0.05, and then we just simply say we accept H0 because whilst it's quite a small probability, it's not smaller than 5%. So we'd say accept H0, there is insufficient evidence to suggest the mean mark has decreased. Okay, I'm just going to sort out my screen here a second. Okay, right, I'll just check any questions in the chat. And that's quite a long example, that one. But to be fair, today's lesson is a little bit shorter than yesterday's. So I thought we'd do a bit of a longer starter instead. By the way, just to make sure that when I worked out that probability, make sure you use your sample standard deviation, so 50 over the square root of 12 for sigma. Right, unless any questions, I'm going to move on. I don't think I can see any questions in the chat, so I will move on to tree diagrams. Okay, so something you would have seen before at GCSE, I imagine, but just kind of ties in together all that we've done so far. So we can look at conditional probabilities, which we've been looking at this week, on these tree diagrams as well. So you might have been using tree diagrams all this time, but you probably never thought about it in terms of conditional probability. So you can see there our tree diagram, and what we can do is everything on this second branch we can define as a conditional probability. So for example, here at the top, well, when I have this top probability here, so the one that's highlighted in green, but the first one at the top, now that probability is calculated by looking at what's happened previously. So given that A has happened, what is the probability of B? Given that, and then the second one is what's the probability that B doesn't happen given that A has already happened, and so on. And then we can also look here at the side here, on the right here where I've highlighted, when I work out the probability of all of these events, that, well, probability of A and B, we can just prove that formula that we looked at yesterday, but that's just the probability of A times the probability of B given A. So remember, at the end of these branches, you want to multiply these probabilities when you've got your tree diagram. And it really just nicely kind of brings everything together. We've also got the notation where it's either A or it's not A. So you can see it brings together all that we're doing so far with probability. So let's get into some examples. So we've got a bag, the typical probability example, we've got a bag with beads in it. So we're going to draw our tree diagram. I am kind of assuming we're okay with drawing the tree diagrams, but if there are any questions on that, please let me know. So I've got the bag containing 6 green beads and 4 yellow beads. So the first pick is either going to be green or yellow. There's going to be 6 out of 10, and it's going to be 4 out of 10 for yellow. And then your second pick, yes, again, it's either going to be green or yellow, or green or yellow. So just a quick check, we're all okay with this in the chat then. So this probability where I'm just highlighting here, what should I put for my probability here? So where I've got in blue there. So just see if we all agree. Yeah, 5 out of 9. And that's because one green bead is already gone. So I've got 5 green beads left. But of course, I've took out a bead, so I've got 9 left in the bag altogether. So then just filling in the rest of the probabilities. Okay, here at the bottom, I could put 2/3 and 1/3. I'm just going to keep everything in ninths here. And then if I want to work out the probability of a green and a green, or a green and yellow, yellow and green, yellow and yellow, then I just simply multiply these together. So at the ends of these branches, I'm just going to multiply together. And here I get 30 over 90, or 1/3 if you will. Now, it's not always necessary to write down all the probabilities, but I'm just going to do it for this first example. So I've got all my possibilities there, and these will help me in the later part of the question. So this actual question that I'm asked is, given that both beads are the same color, find the probability that they are both yellow. So what I'm trying to work out is the probability that they are both yellow, given that they are the same color. So what this would be, if we think back to our formula yesterday, well, on the bottom of the fraction, let's just think of it as the formula that we learnt yesterday. If we want the probability of A given B, then we do the probability of A and B divided by the probability of B. So what this means for our question here is, on the bottom of the fraction goes the probability that they are the same color, and on top of the fraction goes the probability that they are both yellow and they are both the same color. So on the bottom of the fraction, I have to put the probability that they are the same color. Okay, that's restricting my sample space to that. So the probability they are both the same color, I just add the 30 over 90 and the 12 over 90 together, okay, because that's, if they're the same color, they're either both green or they're both yellow. So I add the 30 over 90 and the 12 over 90 together. And on top of the fraction, the probability they're both yellow and the same color. But there's only one scenario where they can both be yellow and both be the same color, and that's just simply if they are both yellow. Okay, both conditions have to be met, but obviously if they're both green, then they're not both yellow. So 12 over 90 on top. So I simply just work out that fraction, and I get 2/7 when I do that. Okay, let me know if there's any questions that you have. And we'll go into our second example. So I've tried to get in a lot of our new notation. I know setting up the tree diagram probably isn't something new, but it's important that you kind of think about this new notation and also the conditional probability. That's the bit that can catch people out. Just make sure you read the questions carefully here. So in the next question, that's question with vaccinations and flu. This is nothing to do with current events. We've been using this question for the last few years. I just want to say as a disclaimer before we begin with this one. A GP practice encourages elderly people to have a flu vaccination each year. The doctors say that the vaccination reduces the likelihood of having the flu from 40% to 10%. In the practice, 45% of elderly people have the vaccination. So the first thing we do is draw a tree diagram. So the first scenario I should look at is, do they have the vaccination or don't they? So V and V dash. And to be fair, probably the hardest part of this question is just setting up your tree diagram correctly. Once you've got your tree diagram, it really puts everything in place. It makes the question a lot easier. So 45% of them have the vaccination. So I'm going to put 0.45 here. So therefore 0.55 don't have the vaccination. So then, if they have the vaccination, they either get the flu or they don't get the flu. Now, if they have the vaccination, there is a 10% chance that they get the flu. I put a 0.1 here, meaning if the 10% chance they do get the flu, there's a 90% chance that they don't. And then same scenario here, but different probabilities. If they don't have the vaccination, there's a 40% chance that they get the flu, and there is a 60% chance that they don't. So now I've got my tree diagram all set up. I'm going to start to work out some of these probabilities. Now, for the first part, we're working out the probability that they get the flu. So what I'm doing is work out the probability of F. Now, there's two scenarios how they can get the flu. Either they have the vaccination and they get the flu, or they don't have the vaccination and they get the flu. So what I'm going to do is work out that first scenario, work out the probability of that first scenario, and just do 0.45 times 0.1. So what you're looking at there is saying 45% of people have this vaccination, and then of those 10%, they actually get the flu. So 0.045 people get the flu, given that they've had the those that have had the vaccination. The 0.045 of them get the flu. No, I said that wrong. Of the whole population, it's 0.045 are made out of people that had the vaccination, the flu. There we go, got there eventually. And then the other scenario is that they don't get the vaccination and they get the flu. So we multiply those probabilities together, and that takes up 0.22 of the population. So then we can just simply add those probabilities together. So I'll do that in a bit more bold, so you can see clearer. Okay, and then we get our final answer there of 0.265. Okay, so it's just adding up the probabilities where they get the flu, and there's two different ways that can happen. Now, part 2 says probability they get the flu given that they have the vaccination. Okay, so I'm just going to throw this question out. This would pretty much just be a 1-mark question if it's in the exam. So in the chat, can you tell me what probability you would get? So the probability that they get the flu given that they have the vaccination. Do we all agree with 0? So a lot of people say 0.1 or 1/10. Okay, and you are right. If you put 0.1, we'll just look at this probability here. Okay, it's the probability that F happens given that V has already happened. Okay, so that is just 0.1. Okay, someone's chance of getting the flu is greatly reduced based on if they've had the vaccination already. And then finally, we're looking at the probability that they had the vaccination given that they get the flu. So this is V given F. Now we have to be careful, it's simply not just 0.1. We can't just rewrite that again. What we have to do is use our formula, and that's that we're looking at the probability of V and F happening given the probability that F has already happened. Okay, so remember, when you do that formula, these two letters should match. So the probability of F, that's what we found in part 1. And then the probability of V and F, so the probability they have the vaccination and the flu, well, that's going to be the 0.045 from the result of that first part there. So we can just work that out, simplifying that fraction, and we get 9/53. as so. Okay, let me know if you do have any questions. We'll quickly go through example 3. Example 3 should really be a very quick one. So I'm just going to go through the notes here just in case you weren't sure. But yeah, with that last question, just be very careful that you read everything very carefully. So the last one. So on my way to college, I drive through 2 sets of traffic lights. The probability that I'm stopped at the first set is 0.7 and the second set 0.4. So what I would do to set up my tree diagram is I'd have something like this for the first branch. So S for stop and S dash for not stop. So the probability that I stop is 0.7. The probability that I don't is 0.3. And at that second set, I've got 0.4, 0.6. These probabilities will be the same for both scenarios because you are told they're independent. So the probability that you're stopping at that second set, it doesn't matter what happened at that first set. So the probability that you stopped at both sets, well, that's simply just 0.7 times 0.4. So we simply just get 0.28, the probability that you stopped at both sets. And the probability that you stopped at least once, well, there's a couple of ways you could do this. You could work out all 3 of these probabilities where you either stop twice or just stop the once. So either stop at the first, but not the second, or don't stop at the first, but stop at the second. Add all 3 of those numbers together for 0.82. Or alternatively, the probability that you stopped at least once, well, what that means is that you haven't not stopped. Okay, so the probability that you don't stop at either would be 0.18. So we can simply then just do 1 minus 0.18 and we just get 0.82. Okay, I have gone through that example very quickly, but I think that's probably the easiest of the 3 that we've got. So if you do have questions, if you go through it too quickly, please let me know. Otherwise, I'm just going to move on to the very final bit, which is the Venn diagram. So we've used a tree diagram here, but we could also put this in the Venn diagram. So the first circle will be stopped at the first set. The next circle will be stopped at second set. Now, you're told that these probabilities are independent. So you know that what happens at the first set doesn't have any impact on what happens at the second. So if you want the probability of stopping at the first and second set, that's just going to be overlap of these 2 circles. We can simply multiply these probabilities together because they're independent. The probability of A times the probability of B equals the probability of A and B. So you know a 0.28 goes in the center of that circle. The first set, that circle all has to add up to 0.4. So you're going to, 0.7. So you're going to need a 0.42 there. And then the second circle, it all needs to add up to 0.4. So we just need a 0.12 there. Finally, the whole thing needs to add up to 0.18. So I need to put a 0.18 on the outside. Make sure with your Venn diagrams, by the way, you put a rectangle. A lot of feedback I've been given on the homeworks is a lot of people haven't been putting the rectangle around. It is going to lose your mark, okay? Don't lose a really easy mark to lose there. Right, so that is the tree diagrams. When we come back after Easter, we're going to look at distributions. Okay, so that you might be looking at the booklet ahead of the booklet and thinking that looks a little bit different. So whilst this might seem a bit familiar with the tree diagrams, the next bit might need a little bit more explanation. So we'll see you back here after Easter. I believe it's going to be Tuesday is going to be the first lesson back because Monday was technically always a day that you never were coming back into college. So it actually be Tuesday where we'll do the first lesson back, and we'll do Tuesday, Wednesday, Thursday, Friday. Sorry to kind of keep messing with the structure. Next thing to do though is have a go at the questions. Okay, so get in the habit of do a lesson like you normally would, and then do some questions like we normally would. Please let us know if you've got any questions, whether that be about this, anything we've done previously, the homeworks. I've put up a video, if you've seen on Teams, for how to do question 3 on the normal distribution homework, because that was one that people struggle with quite a bit. But please do let us know if you've got any questions, any way that we can improve these lessons, improve these videos, whatever. Your feedback's really helpful. I'll just stick on the chat for a little bit longer, just see if there's any questions right away. I'm going to stop recording here.